Hello, everyone. Before we begin talking about the abstract, I want to declare that I, Grant Baker, am an employee of Med Institute Incorporated, a company that conducts MRI safety testing and computational modeling and simulations for numerous medical device companies. This abstract is on the potential safety advantages for patients with medical devices and low magnetic field strength MRI systems. MRI is a growing medical imaging modality, with millions of scans being done every year and the number continuously increasing. As MRI continues to gain popularity and to be used more frequently, it is important to ensure the safety of patients being scanned. One way this is done is by evaluating the safety of medical devices in the MRI environment. For electrically passive devices, especially implants, this evaluation addresses the magnetically induced force, torque, image artifact, and RF-induced heating of the device. The purpose of this research was to evaluate and compare the safety of medical devices in high field and low field MRI systems in terms of these metrics. The 3 Tesla and 1.5 Tesla MRI systems on the left were used to evaluate device safety in higher field MRI systems, whereas the 1.2 Tesla open bore system and the 0.55 T system on the right were used to evaluate device safety in low field MRI systems. The static magnetic field of each MRI system was mapped in 1 centimeter increments starting at isocenter out towards the control room using a Tesla meter. These measurements were then used to calculate the spatial field gradient. The force product at each measurement location was calculated as shown on the slide. The maximum force product for each MRI system was then used as the magnetically induced force metric, since this is where devices would be tested according to ASTM F2052, and because the force product is directly related to the magnitude of magnetically induced force of a given medical device. The Tesla meter reading at isocenter was used as the evaluation of magnetically induced torque for devices in each MRI system, since devices are tested for torque at isocenter according to ASTM 2213. The magnetic field strength at isocenter is directly proportional to the magnetically induced torque of a given medical device in an MRI system. 3 commercially available medical devices were used to evaluate image artifact and RF-induced heating of the various field strength MRI systems. These included a knee and hip prosthesis from Exactech and a cardiovascular stent from Cook Medical. Image artifact testing was performed according to ASTM 2119 for each of the devices at each of the field strengths. Gradient echo and spin echo scan sequences were conducted with a 10 millimeter slice thickness. Images were evaluated for the worst case artifact distance, which was calculated as shown on the slide. RF-induced heating of each device was evaluated according to the ASTM 2182 standard. The devices were submerged in a gel phantom with temperature probes positioned as shown in these images. Temperature rise after 15 minutes of scanning was compared for each device at the various field strengths. This slide displays the results from the magnetically induced force and torque evaluations. The magnetic field strength at isocenter was measured to be what was expected for each MRI system. Torque will be less evident for the devices as the field strength of the system decreases. Magnetically induced displacement force increases in magnitude as the maximum force product increases. Keeping that in mind, these results depict that the potential for magnetically induced force of a device increases with increasing field strength of the MRI system, with the exception of the 1.2 Tesla open bore system in the second row. The worst case image artifact for all devices occurred with gradient echo scans. An example of the worst case image artifact for the knee prosthesis at each field strength is shown in the figure on the left. The resulting artifact distance for each device at each field strength is shown in the plot on the right. These results depict that image artifact of the devices increased with increasing MRI field strength, or stayed the same as it did between 0.55 Tesla and 1.5 Tesla for the stent. All maximum temperature rise results were scaled to a whole phantom SAR of 2.0 watts per kilogram, besides for the 0.55 Tesla results, since experimental measurements indicated that the RF amplifiers are not capable of achieving a whole phantom SAR of more than 0.45 watts per kilogram. Comparison of the maximum temperature rises and of the temperature time plots for each device show that low field strength systems are able to reduce RF-induced heating for devices. For all devices, the low field strength scanners had the lowest heating, and the maximum temperature rises were typically significantly lower than for the higher field strength scanners. Results from the study depict that all tested MRI safety measures were more favorable for devices in low field strength MRI systems than they were for devices in higher field strength MRI systems, with the exception of force in the 1.2 Tesla system due to its open bore design. This indicates that low field strength MRI systems have the potential to provide safety advantages for patients that have medical devices. These systems are able to provide adequate image quality with less powerful RF amplifiers, resulting in reduced RF-induced heating for patients with medical devices. Improved safety and lower image artifact in low-field MRI systems can allow more scanning of patients with devices and can provide new opportunities for interventional MRI procedures.